It is a great pleasure to introduce the 2016 Heinemann Award, Professor Paolo Fornasiero. Professor Paolo Fornasiero is still very young, was born in 1968 in Switzerland, but then he moved to Italy and studied in the University of Trieste, where also he obtained a PhD in heterogeneous catalysis. He then stayed 1 year as postdoctoral fellow in Catalysis Research Center of Reading, and then was appointed as a professor in the University of Trieste, where he still and has a professorship in inorganic chemistry. He received many awards, and I like just to introduce two. One is Nasini Gold Medal in 2005. This was for his work in inorganic chemistry, and then he received also the Cusoli Gold Medal in 2013 for this work for catalysis. So this is a well example of how he was always bridging inorganic chemistry and catalysis for a really excellent work. In 2015, he also became associate editor of IACS Catalysis. He published more than 200 papers, and he is also very high H index, and also he is associate researcher of the National Council of Research in Italy, and he leads the unit of chemistry of organometallic compound in Florence. Paolo, the floor is yours.
Thank you very much. I want to start thanking the selection committee, Professor Avellino Corma, Professor Kan Lee for the award. It's really an honor. Also looking at the previous recipient, it boosted my career for sure. It put lots of pressure. I do believe it is also recognition of what it can be done also in a small lab like mine in a poor country like Italy, especially today after the football match we lost against Germany. I'm going to talk about nanocatalysis in energy-related application, but let me start saying a few words about Heinz Heinemann. He was really a great scientist. I want to point out a few aspects which in some way are linked to my career. As you notice here in the list I made, he worked a lot on petroleum chemistry, valorization of coal, which are energy-related aspects as the topic of my talk. And another important aspect is that besides having very excellent fundamental papers, he also had a very tight connection with companies, as you can observe from the high number of patent and commercial processes he was involved in. So this is also what I do believe we have to do. We have to improve the quality of our life with what we do, and catalysis, I hope to demonstrate today, can do really a lot in this respect. I want also to point out that he was co-founder of the Philadelphia Catalysis Club, and I have lots of collaboration in Philadelphia. I will mention this at the end of my talk. We are here also thanking to him because he was also a co-founder of International Congress on Catalysis. Unfortunately, he passed away in 2005, which for my career is a very important step. I became independent. I got the first big award, as Gabriele Centi mentioned. Got my first science paper without supervisor. So in some ways, these dates are also important for me. Just a couple of slides on where I come from. This is Trieste, the main square of the city, seaside town, and Trieste is north Italy, close to the border to Slovenia. We have a very large quay and the largest regatta in Europe with over 2,000 boats at the same time in the Trieste Gulf. So I will start my talk giving the motivation, a brief introduction of my work, and then I'll divide the talk in two parts. The first will deal with nanocrystal to prove the importance of the metal support interface in CO oxidation reaction. Then I'll try to explain how we can boost the activity in methane oxidation by enhancing the interface between the metal and the support. Then I'll come back to the story of nanocrystal, try to show you the advantage of using this approach in biomass transformation. And the second part of the talk will be dedicated to photocatalysis, mainly for hydrogen production, dealing with different systems, iron oxide, titanium nanocrystals, and carbon-based hybrid material like those reported here in this tomography. Well, in the last century, we have seen many innovation, technology. Of course, we went to the moon. Transportation has seen a major advancement. We have the internet, the technology to get connected anytime. But if you look really, which is the most important innovation of the last century, which had a major impact in human society, you have to look at the human population. And you can appreciate here, along the time, the population was slowly growing, but then at a certain point it started going up. And then this growth was really exponential. And the reason for that was the discovery of guano, a very useful fertilizer. Of course, they realized immediately that it was very important for agricultural purposes. However, the resources were limited, so they started to look at more guano and so on. But chemists at that time had a great opportunity to make what today we call the Haber-Bosch process. So the ammonia process, the fertilizers, and those had a major impact in the production of agriculture. For instance, this is the maize, which has a step increase in the United States. And so the population was allowed to grow. So chemists and catalysis has this great possibility to change our life. And what is the situation today? Well, today our society is energy-based. You can see here the energy consumption per capita in 2014, how much energy is required for the north part of the Earth, especially in the United States, also in Australia. And we know that there is a direct link between the quality of the life, here the Human Development Index, and the availability of energy. So we expect still an increase in energy demand in countries like Africa, South America, but also in Middle East, in Asia, where, of course, quality of life can still be improved. So our society is still based mainly on fossil fuel, which produce pollutant, just focusing on CO2, but particulate, NOx, SOx, and so on. And these are spread all over the world thanks to the wind. And so we have to think about these environmental energy-related aspects. And for sure, we have already faced the end of the cheap oil in the sense that we have to put more energy to get oil out from the reservoirs. In the past, it was quite easy. You could get 100 barrels of oil, just put in 1 barrel of energy. Nowadays, it's much more difficult, and you can have a ratio 10:1 as an average situation. So I guess we can agree that sooner or later we will see an energy crisis, a situation. And being in China, let me do this joke for you. Hope this is correct. In the Chinese hydrogram, crisis should be written in this way. And you can split this in two parts. The first one means danger, but the second one has also the meaning opportunity. And I do think catalysis has really a great opportunity to solve this problem. And so one of the key idea for catalysis to replace this oil to CO2 process, which also involves pollution, with something which starts from CO2 going to, for instance, cheap fuels. But of course, you need hydrogen, and this must be done by using renewable resources, renewable energy in a carbon-neutral energy water environment. And catalysis can play a major role here, as in other important catalysis process. So let's see how we can design a catalyst. There are essentially two ways. One is the traditional way. You prepare different material, you test them, you identify the most active one, and then you look with all the sophisticated techniques, operando atomic resolution microscopy, to identify the active sites. However, as we overview a couple of years ago in this article, you can also take advantage of the nanotechnology. We know we can prepare monodisperse material which has exactly the same shape, dimension, forms, and having this library of precise materials, you can have a much clearer correlation between catalytic activity and structural parameters. Just to show you what I mean for this kind of Lego building blocks that you can use to design catalysts, here are some examples. You can have long bricks, spheres, or you can also combine in core shell type material and so on. You can have polyhedra, you can have cubes, and so on and so forth. Just from the literature, I will show you a nice example from Gabon Samojai work in which they prepare Syria cubes connected to platinum cubes on a silica substrate. This is the cartoon, real TM images. And if you have this right order, you can indeed perform a methanol decomposition followed by hydroformylation reaction, obtaining propanol. If you have different order of the same component, platinum, Syria, silica, in this tandem reaction, you do not form propanol. So two important messages, the interface between the oxide and the metal is very important, and also the order of this component. So we have done a lot of work also in the area to understand the role of the metal support interface, and in particular we have prepared monodispersed nanocrystal of different catalytically active metal like nickel, palladium, and platinum, obtaining, let's say, small or medium or large particle depending on the reaction condition. These nanocrystals are all equal in size, and the difference might be just one atomic layer, so are really mono-dispersed. And then having this library of protected nanocrystals, we decided to deposit on two types of supports. An inert support like alumina, and a reactive redox support like cerium dioxide. And after gently removing the capping agent, we test this catalyst for CO to CO2 reaction. And the results are reported here. You can see that on alumina, the nickel is less active than palladium and platinum, as expected, as well known. And in the Arrhenius plot, you do not see a size dependence. Different is the case on cerium dioxide, where you can already appreciate the higher activity, the shift in the light-off temperature to lower temperature. Nickel is still less active than palladium and platinum, but in this case, you can observe that there is a size dependence, small nanoparticles being more active than medium and then large. So having this precise type of material, we were able to correlate the fraction of sites with the diameter, and this is the correlation of the surface atom with the diameter. This is the correlation of these atoms, fraction of atoms at the interface with the diameter, and this is the atoms at the corner at the interface with the support. And then we plot the turnover frequency, the catalytic activity against the diameter, and the trend fit pretty well between the two lines indicated that the reactivity in CO oxidation, this type of material, really occurs at the interface, and probably the most active sites are those at the corner. So we have to maximize the interface, we have to optimize the number of these sites to enhance the performances of this catalyst. And to do that, we have designed a new approach to make catalysts we call embedded catalyst, in which we prefer preformed metal nanoparticles, and then we surround this metal nanoparticle by a porous layer of an oxide, porous to allow reagents to diffuse to the surface and products to diffuse back to the gas or the liquid phase. So the contact between the support and the metal core is in a 3D shape. This is not a unique approach. Ferdi Schütz, Edmond Zhang, even Jose Rodriguez in his inverse catalyst are doing pretty much similar work. We have proved in the last couple of years that this is a general methodology to make different type of catalysts, changing the metal, platinum, gold, copper, ruthenium, even rhodium, and different type of oxide from Syria, titania, zirconia, all work up to just a couple of days ago work on platinum silica. And always we found improved activities or stability or selectivity. So let me show you some example of what I do believe is a very elegant approach. And I'm going to talk about palladium at Syria structures. So we prepare protected metal nanoparticles thanks to the strong interaction of thiols with palladium, but this is true also for platinum, gold, and we use acidic thiols which can coordinate a metal alkoxide in such a way that if you do a control hydrolysis in the presence of dodecanoic acid, you end up with this type of units in which you have a metallic core surrounded by units of Syria, in this case, or cerium hydroxide. And thanks to these hydrophobic tailings, these units are highly dispersible in organic solvents. So you can have this stable dispersion, and you can impregnate a stable scaffold. And the first type of application we thought for this type of catalyst was in solid oxide fuel cell, where in the anode you have palladium at Syria catalyst that has to activate the fuel, being methane, hydrogen, syngas, and so on. But the high temperature at which this catalyst operates makes sintering of this catalyst, and so you lose the catalytic activity. And you have to cope with that, just adding more and more metal, which is precious, rare, expensive. So we thought that our embedded catalyst has a much higher stability, and we compared the performances of palladium-only technology with palladium Syria prepared in a conventional manner and our system. The remaining part of the solid oxide fuel cell is exactly the same in all cases. And we observed the performances on fresh material and after high temperature calcination, simulating long aging of the solid oxide fuel cell. And you can appreciate here, for instance, that palladium-only technologies leads to a significant deactivation. The impedance arcs change dramatically, and this is consistent with what we observe as an increase in the palladium dimension. In the case of palladium Syria prepared in a conventional manner, this deactivation is much reduced thanks to the strong metal support interaction in Syria, but still present, as observed also in the increase in particle size by microscopy. For our palladium at Syria catalyst, the system seems to be significantly more stable, opening really application in this type of catalysis. The second very important application for this type of material is in controlling the emission of methane. Methane is a greenhouse gas, has a 25 times higher greenhouse effect than CO2. And methane is released in many applications, from diesel car, from burners, from methane cars. And there is great concern. Indeed, for instance, you can notice here from a picture from the satellite. In this area, this is a rural area, so these lights are not due to the position of a city, but it's just burning methane which cannot be used. In some cases, they are burning to reduce the pollution, the greenhouse gas. In some cases, methane is fitted back in the ground to help oil to come up. However, if you look at the map in the United States, there is unexpected release of methane. And there are questions about fracking that makes some methane coming out. So we have to try at least to control the emission of methane where we can. And for instance, diesel cars are emitting quite a lot of methane, and their temperature is not that high to activate methane, which is a stable molecule, but with a suitable catalyst, we can at least control those, as well as in burners, houses burners, where you use methane. So the most active catalyst for methane oxidation is palladium oxide. Unfortunately, when you go up in the temperature, palladium oxide decomposes to palladium metal, which is not active. So this leads to deactivation of the catalyst due to the formation of palladium metal. And if you cool down the catalyst, it's quite difficult to be back reoxidized from palladium metal due to kinetic limitations. So it's really important to keep palladium in an oxidized state, and cerium dioxide is really doing a great job in this respect, as you can read in this nice book published by Alessandro Trovarelli and myself a couple of years ago, or in this recent ChemRev. What is the purpose of cerium dioxide? Cerium dioxide can reduce this deactivation effect by giving lattice oxygen. So cerium gives oxygen from its lattice, is reduced, can be back reoxidized from the gas phase easily, and so the palladium remain mostly in the oxidized state, and so this deactivation is minimized. It's not zero, but it's minimized. And so in our idea, our embedded catalyst in which we maximize the interaction between the palladium and the ceria should work pretty well. So we try to impregnate a stable scaffold with our units. Of course, you cannot use just a regular alumina or zirconia or so on and so forth, because those are hydrophilic and our units are hydrophobic. So you have first to modify the material, making hydrophobic by treatment with TIOS, for instance, and then having this organic stuff on the surface. You can really disperse homogeneously our units, and after calcination you end up really with nicely homogeneously dispersed palladium at ceria units. And the performances of these catalysts are really good, as you can observe here in the Arrhenius plot with respect to the state-of-the-art catalyst. But very importantly, not only you can activate methane at very low temperature, at high space velocity, so interesting for real application, but you do not observe this deactivation here at high temperature, which was related to palladium oxide to palladium metal decomposition, which means that CO2 is really effective in giving lattice oxygen to palladium. And of course, those are very stable under dry conditions, but as nicely pointed out by Bob Farauto in his comment to our article in Science, we have to also to take into account real situation in which you have water vapor, phosphates from lubricants, SO2, which are expected to deactivate the catalyst. So we did a lot of investigation on the effect of these nasty components. And for instance, the effect of water is quite dramatic. You can observe a shift in the light-off temperature from low temperature to medium temperature, still interesting for application. But in this case, we observed also deactivation at high temperature. So in some way, we are destabilizing the positive effect of Syria. So we were very much interested in understanding why we observed this deactivation. So we perform a steady-state experiment. You can see how quickly is deactivated the catalyst, completely killed in the presence of water. If you remove water at 600 degrees Celsius, you recover slowly and partially the activity, but still the catalyst is deactivated. And we did a lot of investigation to understand what's going on. And basically, we observed that we form stable OH groups in this catalyst, which are removed only by high temperature treatment. We did chemisorption measurements that proved that we reduce a little bit the accessible metal surface area, but not to explain the full deactivation of the catalyst. And only operando exospectroscopy tell us what was the reason of this deactivation. So at high temperature, 600 degrees Celsius, under dry condition, the catalyst is stable, methane is fully converted to CO2, the spectra, the Xenon spectra doesn't change with time, and is fully consistent with palladium oxide, the active phase. Vice versa, in the presence of water, high temperature, same condition, you see there is a change with time of the Xenon spectra, and basically you transform palladium oxide to palladium metal, which is not active. So our explanation, and we got the cover of ChemCat-Chem, basically is that at high temperature in the presence of water, you form stable OH groups that basically block the oxygen transfer from Syria to the palladium, which then remain in the metallic state, is not back oxidized by oxygen from the lattice due to the structure, the core shell structure of our catalyst. So to design something which is stable underwater, we have to think about another oxide which still gives some oxygen to the palladium, but is not forming these stable OH groups. And really, we end up with a catalyst which is less sensitive to water effect, still partially deactivated, and this is zirconia containing palladium system. So let's see the effect of the other poisoning gas. To do that, in the case of phosphate from lubricant, we design model catalysts and we deposit our units on graphite substrate, and we perform what I call close-to-site spectroscopy. Because this is my university here. This is the electrosynchrotron in Trieste, so it took us a few minutes to go from the lab to the synchrotron. And so we basically prepare two types of samples, model sample, palladium at Syria deposit on pure graphite, and on phosphate containing graphite as a control source of this poisoning component. So the operando techniques tell us that basically under dry conditions the catalyst is stable in the absence of phosphate, and there is the deactivation as we already observed in the presence of water. However, if you have phosphates, even under dry condition, the catalyst starts to be deactivated. However, if you have co-presence of water and phosphate, the catalyst is completely killed. And we did lots of investigation to understand this phenomena, and basically all the techniques tell us that in the presence of water, high temperature, and phosphate, you form stable cerium-3 phosphates, which really covers the surface. You do not see anymore the signal of palladium, which is really buried inside the catalyst. And Syria is not flipping between cerium-3 and cerium-4 plus, so there is no catalysis involved in this system. Then we look at the effect of SO2, which is also a very serious problem for this type of catalyst, and we move from this original simple model catalyst to something more sophisticated, more close to the real catalysis. So we start from indium tin oxide. We cover by atomic layer deposition films of alumina, and then we impregnate this time with core shell units of palladium at zirconia, Syria, and Syria zirconia, and after calcination we obtain something which is rather similar to the real catalyst. And the effect of sulfur is very dramatic. At low temperature, you kill the activity of the palladium, you form palladium metal, palladium sulfate. However, at medium temperature, the effect is not that dramatic. It involves basically the shell, zirconia being less deactivated than Syria and Syria zirconia. And also if you remove SO2, the reactivation with zirconia occurs much more quickly and easy. So as a summary, Syria is good to keep the palladium oxidized, but it deactivates with water, with SO2. So trying to make the catalyst more resistant in these harsh conditions, we decided to make a test by covering our palladium Syria material with an atomic layer deposition of zirconia. And we just proved that it's valid for water gas shift reaction and should be valid also for methane oxidation. And we proved that the sensitivity towards SO2 and water is much less significant. So this opens new perspective for real application under severe conditions. Just mention, there will be a specific topic on Friday on this aspect from colleagues from the University of Michigan. They investigated our palladium Syria material in their very nice environmental TM, and they pointed out that the system is much more complex than what we thought at the beginning. And indeed, you can observe here in this TM images with time at high temperature, 550 degrees Celsius, that there is a change. These are clouds of Syria atoms that moves, and so you have a reconstruction, especially at high temperature. You still form some big Syria particles, some large palladium particles, but very importantly, to justify the stability of the activity of this catalyst, many structures remain very small where you have always palladium in contact with Syria, and silicon can have also a role as improving the redox property of Syria. So let's go to this talk on Friday. A couple of words of the opportunity of nanostructure material, nanocrystal in biomass transformation. So this is a very important task. We know how much effort, also here in this audience, there will be a nice presentation to try to sustainably transform biomass in very interesting platform molecules to do chemistry. This approach is completely different from the conventional oleochemistry, where you start from very simple molecules, you go up in the complexity. Here you start already from something very complex, and you have to break and down bonds, and so the selectivity is really an issue in this respect. And we were very much interested in reaction, HMF to DMF, but of course the catalyst which can transform these two, promote also sequential reaction like those that leads to the production of these products in red here. So if you want to selectivity, you have to slow down this type of reaction. But if you feed DMF on the catalysts that do the first step, like platinum and cobalt, they, of course, are still active. So we were interested in see what platinum-cobalt alloy can do. Thank you. Can do, and indeed we managed to prepare a crystal of platinum and platinum-cobalt, different composition. As I mentioned, platinum is not selective. We did this in flow, and you can see that the amount of products depend on the working condition, but still you get this sequential reaction. If you use a platinum-cobalt alloy, you get something which is really selective, and you slow down this reaction significantly. And you do not just increase the selectivity here, but if you go higher in the temperature, you have also an advantage in terms of stability. You see here the platinum deactivates within few hours, while the platinum cobalt remain, the activity of platinum cobalt remain stable much longer. And you can also control the composition by playing with the ratio platinum cobalt, as well as this approach is rather general. You can substitute cobalt with nickel, zinc, or copper. So there's plenty of room in this direction. The second and more probably short part deals with photocatalysis, which is really a green process as it takes advantage of the solar light to promote a catalytic process. So we have done lots of work in this direction involving plasmonic gold nanoparticle nanocrystals. I'm going to talk about this in a few minutes. Very complex systems, supported system, as well as dye-sensitized type of material, which just got the cover page in ChemCom a couple of days ago. So let's start from the first example, which is iron oxide. Iron oxide should not work as the position of the conduction band is below the energy requirement for proton to hydrogen reduction. But we know that in nanocrystals, if you go nano, you can increase the band gap and you can enhance the position of this conduction band. And as nicely shown by Emily Carter from Princeton, iron oxide should work. So far it has been used a lot by Michael Gretzer, for instance, for oxidation reaction, but we managed to obtain supported polymorphs of iron oxide, included hematite, and the trick is to make not bulk material, not dense film, but this type of pyramid-like tips, in which you have a mixture of iron 2 and iron 3. And indeed, if you do that, you can get photocatalytically hydrogen. This is right after an initial induction period, you get bubble of hydrogen. And the amount of hydrogen strongly depends on the type of polymorphs, as well as the stability. In the case of hematite, you have leaching in solution of iron. The solar to fuel efficiency are quite low, but this is just a proof of concept that you can get hydrogen with this type of material. Of course, you can cheat and you can give quantum efficiency of about 20% if you use UV light in the right excitation light. You can also add plasmonic gold or silver, and you can increase the amount of hydrogen you get even in pure visible light. Keeping in the photocatalysis area, we did lots of work on nanocrystal with the idea to understand which of the facets is really involved more in the reaction we were looking at. And by playing with the type of co-surfactant and metal precursor, we obtained this nice monodispersed crystal of different phases. This is anatase, this is bruchite. I come in later on that aspect. And if you look just the anatase phase, you can have these different shapes having different ratio of the 101 and 001 facets, just from pure 101 phase to a mixture 50-50. And you can see the amount of hydrogen you get strongly depend on the facet you have. So this is a way to understand how design more effective catalysts. Very recent work on the bruchite structure. In this case, we prepare nanorods of bruchite, same thickness, and we were able to change just the length of the nanorods from 20 to 50 nanometers. And those are really homogeneous materials. We deposit a co-catalyst, platinum nanocrystal, tiny amount of platinum. These are the high resolution images of the nanorods, and this is the material after use. where you can still appreciate the platinum nano catalyst, as well as the shape of the Brookite nanorods. And the results were very much interesting in the sense that the amount of hydrogen you get strongly depends on the length of these nanorods, even normalizing by, as you have to do, by the surface area. And this is related to the fact, as we proved by EPR and fast transient absorption spectroscopy, that you significantly enhance the lifetime of electron holes by playing with the anisotropy of this nanocrystal. So we do believe that this is a general approach to enhance the photocatalytic activity. The last part of the talk is dedicated to hierarchical hybrid material, in which we combine a carbon-based material with our embedded metal nanoparticles inside an oxide. So the idea is to enhance significantly the surface area of the material, as well as take advantage of the metallic nature of the carbon structure, with the idea to enhance the lifetime of the whole electrons we photogenerated during the photocatalysis. So these are the first multi-wally carbon nanotubes that we used, and effectively we were able to cover nicely with different types of oxide and metals. This is not a trivial, a simple approach, as indeed you cannot just oxidize them, because you want really a tight contact between the components. You do not want naked nanotubes, naked carbon nanostructure, and oxide not in contact with the nanostructures, with the nanotubes. So you have to design carefully the approach, and we did by two reactions. We functionalized the carbon nanostructure nicely, and we were able really to have a homogeneous material. Just to show you very recent work, we use a fancy carbon-based nanostructure like this carbon nanocones. We englobate with our core shell strategy protected palladium nanoparticles, titanium precursor, core shell, and this is really the images of the nanotubes covered by all the components: palladium, titanium, oxygen, and carbon. And this can be extended to many other fascinating structures: carbon nanostars, nanohorns, and so on and so forth. And really, the amount of hydrogen you can get from this hybrid material is significantly higher with respect to the single component, especially when you compare this in terms of surface area of these materials. Last aspect I want to point out that in our research we always had a look at environmental aspects, and so we have done lots of work also in the area of recovering material from spent catalysts, like recovering noble metal from car converters. And we designed, we patented, and just published a process in which we can extract palladium in quite mild conditions, obtaining this type of complexes that are also very useful in preparation of photocatalysts, which show very high hydrogen evolution, thanks to the possibility to incorporate in the catalyst part of these components as sensitizers. And the last very important aspect for us, dealing with nanostructured catalysts, we look also at toxicity or skin permeation of these nanoparticles, as just reported a couple of weeks ago in this paper. So saying that, I hope to have been able to convince you that we gave a contribution to a better quality of our life by manipulating catalysts at nanoscale level trying to make hierarchical catalysts, boosting the metal support interaction to have more efficient, stable catalysts. And of course, I have to acknowledge all the members of my groups. These are young people, and in particular, Tiziano Montini here, Valentina Gombach for photocatalysis, Matteo Monai for the Korschall effect with sulfur, phosphorus, and water, Michele Melchiona for the last part on hybrid material, and a special thanks to Matteo Carniello, who now is assistant professor in Stanford, who did a lot of the work, as you have seen from the references during my talk. And of course, I have also to thank many friends and co-workers, among all Ray Gorty, good friends, and Chris Murray, both from UPenn, Maurizio Prato from the University of Trieste for the carbon-based story, Davide Barreca for photocatalysis, supported photocatalysis, financial support. I want to have the opportunity coming from Italy also to mention that next EuropaCat will be held in 2017 in Florence, beautiful city, at the end of August. So please take note of this event, and thank you very much for your kind attention.